Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and welcome. Today we will continue making the disassembler, and if you'd like to ask some questions, you can post them on Twitter or YouTube, and I'll be there to answer. With that said, I would like to start with this and open the project. Let me close all this stuff. And I like to compile it, and while we compile we can just open the debugger as well. Let's see if we do compile. Yes, we do. So if you guys remember, the last thing we did was that we were playing around with a new instruction, which was, I can show you, it's an add instruction which has a special encoding that has the extension table, which basically has an extended opcode, which is just another way to encode it, you know. There's nothing more to it. It's just like a different way to go. It has the same operands, you know, 2 operands, 1 source, 1 dest, and it adds them both and stores on dest. So it does the same stuff, but the source, it was an immediate byte, and destination was a memory operand, which was, it had a specific memory address, you know. So if we go to here, I can show you. So if we run this, you can see the new instruction, which is add EAX plus a displacement, which is a byte displacement. Of course, we probably want to do something like, I don't know if we have, I mean, if we should display that's like this, yeah, which is, which it could be. I mean, it's not like something weird going on here, but yeah. So it's just, well, that we have to do that. It's a byte, so it's okay that we just print it's a byte. But you know, the address, I mean, because if you think about it, we instead of printing the operand, we could print the operand, of course, but since it's in memory, we could say that we have I mean, the memory operand is the one that it's a byte, but the address has an effective address that it's determined by the current effective address attribute. So that's something that we also want to change. But you know, the last thing we did was that we adjusted the brackets, so now they look correct. So we have a register inside the bracketing, which is kind of the syntax of normal assemblers. When you see that, it's that, oh, we know that the register has as as value an address, you know, and that's it. So as well, we have another problem here that you see. Uh, we have this AL plus, which is not correct. These instructions don't have even. I mean, we don't have that possibility. You know, we there's no addressing mode that allows to have AL as a memory operand. So yeah, I mean that's not correct. We have to change that and adjust it. So that was the last thing we did because yeah, so I would like to do that as well. And if you see here, this instruction does, I mean, and that instruction does need to have two operands, and we need to find out what happened to the other operand that should be here somewhere. And so as that, I would like to go into the code and find out. So if you think about the way that we are storing this data, I don't know, I like to see why does that instruction happens not to have that thing. So I think I will start with that. So let me go and do that thing. So I would like to save, since it's the last instruction, I can say this. So C byte, what? No, my bad, it was this one. So C byte, now it's pointing to 0x03, which is correct. This is the last instruction, and I would like to see what happens. It's a 1 byte opcode. There you go, there you go. So if we see the entry, we have a mother RAM, that's correct. We don't have a rectum mother RAM. We don't have an immediate size, that's correct, because this instruction contrasts with the other instruction, add instruction, which does have an immediate size. It doesn't have a memory operand size, and it doesn't have a register operand size. So probably that's kind of bogus, you know, because yeah, we do have a register operand size, and we probably do as well have a memory operand size as well, but so probably that's the problem. But let me see. So we know it's an add, it has two operands, so if we begin the operand instruction, well, I would like to see the C byte is going on 5, that's correct. So it's going on 5, and we're going up to that displacement. So I think the most sure thing to be is that we are adding EAX to the displacement, you know, so we should have EAX as a thing. So let's see. which is there, and well that's okay. Now let's enter here. We have a blah blah blah. Now of course we don't have a effective opening size. Should be 4, and we go into it, and it seems that it already gotten the upfetch count, which is probably not the thing. So let me go back another time. And I would like to see what happens. So we're gonna get there. And here we have an effective opening size, which is null. Oh, and we see this fetch count. We treat it as if we had found it, so that's the problem. So even though, I mean, it would be, I think the problem there is that it should be like that. So we're gonna push a string to buffer. We're gonna fetch a register operand, which has an effective operand size of null, so it shouldn't enter at all. And this is also this is buggies. So let's solve that as well. Well, let me run it first so you can see. So I run things down, and now it happens that we don't have that. Well, now we have the EAX, it appear now, and we don't have the AL, which is we solved two problems on the same side. So yeah, I mean that was pretty much the thing. And now let's solve this plus thing that shouldn't be there. So let's go there and say that, where is it? Fetch register, it's not in fetch, it's in the memory thing. So since we cannot assert this, so we can say this, which is a little bit better because we're already pushing stuff into it. So it's just like if it's greater than 1. So now it's just better. There you go. So yeah, now we have a more decent stuff there. And continue. There you go. So now we have some cleanup there. And yeah, so that's pretty much it. We have our operands, memory operands. This is just displacements. So if you see here, well, this displacement, we have to think about these displacements because how to say it, you know, displacement can and pretty much should, or pretty much they must be the same size to the operand that they are working with. So this is not possible, you know, we cannot have an 8-bit displacement being summed upon the 32-bit register. So this has to be sign extended to match the size of the register which we are working with, which is the case for this one. And for these cases, which they are displacement 32s, so that's okay. They don't have to be extended, sign extended, at least that we know, you know. It all depends on the effective operand size. Since we are talking here, like, I mean, if you think about it, well, we are using addressing modes that are 32 bits, you know. So, for example, here we're using 32 bits. Normally, pointers, well, since they are offsets, that probably is okay. Yeah, well, that's the way it goes, because in the tables, that's the thing we have. So if we go, should remember, if we go to the mother and byte table, which is this one, this is the 32-bit addressing forms that they are allowed, and they pretty much have a 32-bit thing, you know. No, sometimes we have a displacement 32, which is the normal case, the thing that we already tested, and now we have this case, which is a displacement 8, but has to be sign extended. And for example, yeah, I mean, they don't tell us something about if they should be. The only ones that are sign extended are the displacement 8s, and when we are on the addressing form for 16-bit, they also, as well, just the displacement 8 is the one that is sign extended. The displacement 16 is not sign extended. So let's try to add that. It's not super difficult. So yeah, so only 8-bit is gonna have to match the theme that we are working with. So since right now we're working with 32-bit operand size, where is it? So we start with effective operand. I mean, we haven't added anything in 16-bit RCN mode, so we have to test that as well. But we're assuming now we have an effective operand size of 32-bit, you know. And the thing that we are testing on the loop is the address size. So this is the problem. We are testing the address size, which in normal scenarios that's gonna be okay, because that's also something that we use in here. For example, address size stuff. So this is gonna be normally we have an address size equal to 0, or an address size equal to 8, 32. So yeah, I mean this is a little bit wonky. This is also 32. It's sign extended, but it's just the same thing. So 32, 32, and yeah, so that's pretty much it. So the problem is just that since we are fetching it from here, this well, we can say that it's blah, and say and here's the place where we have this index. This 0 is gonna be the thing that we are looking at, yeah. So this is gonna be UNIT byte, and I can say byte and 0x it has to be well, this is the number in decimal, and binary, sorry, in hexadecimal has to be it has to be this. Is that correct? 1248, that's correct, and 0 on the other side. So that's it. So, well, Um, well, we can do this, I guess. And uh, well, yeah, we don't need that. I can just do that. And we're gonna push string. Temp b, temp cam. This is gonna be output for cam, buffer, the buffer size, size sign, one. And we're gonna use the effective address size. And this is gonna depend, but we can say the effective operand size is the one that gets changed here. So let me clean this a little bit. So this is effective address size, effective operand size. So here's the place where we add it. This is a place where we assign it. I like to do this like this. More like this. So there you go. And then we can just say the same. Oh, yeah, I mean, I was just cleaning up the operands there so I can know that which one we're using, and we don't have a collage of variables there. Yeah, so this is the push string thing, and here we're just gonna sign extended. Push string to buffer, out buffer count, buffer size, sign. By a certain amount, of course. So the operand, the effective operand is gonna be okay because we have to match the effective operand. If you think about it. So yeah, I mean, this is a little bit wonky. This is more like uh, like this. Because it's the operand which we're working with. Sorry, the address, not the operand. So it's the address which we're using. So the address is the one that's going to change depending. Like saying, oh, you know, we have a 0, and this is going to be the case where we just like all the time just like go around and use them. Now we cannot use this anymore, you know, because all the time we're using 32-bit addresses, you know. So really we don't care about that. The displacement is the only thing that changes. So it's just like it's more like, and we don't care too much about the operand size, which it would be nice, but in this case it's not the case, you know, because that's the one we used over here. So for the address size, we're gonna use that, and let me put the charger. I can just say here that instead of modifying, thank you, but I don't I don't want that right now. So yeah, I was mentioning here, like instead of modifying the address size here, we probably want to modify just like a displacement. So the displacement is going to be something there, you know, and this can be effective byte size invalid. We can start by there, and you know, depending on, you know, this is where we're gonna play around with here. So the displacement is gonna be the one that changes. So this is well, yeah, it's invalid, isn't it? Yeah, it's invalid. Yes, it is. And then here is a 32-bit displacement. Well, it's an 8. This is like that. And here we're gonna say that the displacement is gonna be 32. The address size but the address size is just the thing we happen to have. We don't need it. Well, it doesn't change at all. But well, yeah, I can use it. Effective add size 32, and operand size, this we don't need it anymore. And here we have to say, hey, we're gonna push, and here we're gonna have the address size instead, and here it's the same, and here is the one we fetch, so that's okay. We push a string, whatever, and then we say if address size, which normally happens to be well, no, this is if displacement, because this is pretty much the displacement that we're currently working in. This is the operand stuff, that's okay. And displacement normally is a 32 thing. Is greater than 0, let's say. And displacement modeling by around sprintf, yeah, we have to do that. Now if address size, effective byte size, well, if displacement is blah, we're gonna use the sign of the displacement, which is a value that we use here. And then here push, we're gonna go from, let's say, address size, and well, here we can go just the other way around. This, and we're gonna push the sign. We can push we can push it 2 times if we want it. We can do this, I guess. And well, I think this is stupid. Yeah, because well, you know, sometimes we can go in the other way around. So yeah, you know, we can go that way, and yeah, there we go. And here we're just gonna be address size -1, and then plus equal then 1, index And then I don't know if we have a sign extension there, but yeah, sign extend. No. Well, if we use it, we can just use this kind of idea here. So for this is the same stuff. If we happen to have a yeah. Well, this is displacement now. Yeah, that's all she say. Here it's just the same stuff, and pushing all around. Okay. Okay, so I think that's a little bit better now. So let's test it. First of all, we're gonna get let's see what happens. Operand, this is it's not that anymore. This has to be address size plus 1, and this is not address size anymore, because it's the displacement that is the one that we decode in there. So displacement of fetch count, and this happens if we successfully discounted it. The other thing that happens is over here we have an fetch count as well. So yeah, that's the thing. So let's see what happens. So we run this, and the first instruction is gonna have an address, and memory operand, so we can see what happens in there. So yeah, we're gonna get into this. Well, oh my god, this is gonna be the same. Here, over here, we can just go and look at the thing. So operand size is 32, address size is 32, displacement is invalid. We have a modern byte, which is something. So this will have an effective displacement of the byte size, and then if modern byte mod blah blah blah, we'll have that assert modern byte blah blah blah. We're gonna push string. We're gonna fetch a register for the effective address size of 32. So we're gonna get EAX, that's correct. Effective operand looks correct, okay. Then we push it plus, we push it, there you go. If displacement, there you go. we have a displacement of effective byte size A, there you go, and we use the sign, and we have a byte displacement if by and 0xa. That means that well, what was the by? Oh yeah, well, it was 0 0, so that's okay. So it's gonna be, the sign is gonna 0, and we can just say that we're gonna go 3 times 2, 6 times, pushing the string, you know, 0 0 0 0 0 0 0, and there you go. And now we care about the displacement. There you go, we push whatever we got there, 0 0. So we have 1 2 3 4 5 6 7 8. Okay, perfect. And there you go, we push the string and operand offset plus displacement plus 1, fetch the register, fetch immediate, by player instruction. There you go. So now we have an effective address, you know, effective displacement that it matches the size of the register, you know, which is nice. So let's see and run the next one. That's correct. Then Fucom and and now we have EVP, which by some reason it shouldn't be there. So let's see what happens. So because now we go back to to something EVP, that's kind of weird, isn't it? So yeah, well, let me try again. There you go. Let's see what happens here. So we got a valid entry. Yes, we do. This is the same. We haven't changed anything here. So let's go and fetch the memory operand. This is well, at least it should be a memory operand. There you go. So the problem is with the memory operand. Okay, so we say that we have oh, it's because the address size now, it doesn't change anymore, isn't it? So we have an address size of 32, and that's because we are using that. So yeah, it's because of the address size. The displacement is correct. It's the one we check and we look for on the other places. Now we match there, and the address size is gonna be 32. So yeah, this is the problem. This is the only little problem. Since yeah, I mean, yeah, because we're dividing from addresses and displacement just because of that. So this is just this. there you go. So yeah, so now we have a proper displacement with its address size being properly padded and stuff like that, which is good. Something nice. And yeah, now we handle both 8-bit displacements, sign extended, and not 8-bit displays. So for fun, let's try to change the sign of the displacement for, let's say, the first instruction, so we can see that it is sign extended. So if we go there and find out the encoding, we're gonna have that the mother RAM, we have 40, and this is 00. This is gonna change to F0, let's say, and that should be sufficient to set the others as F. Okay, and that's correct. Yeah, now I see the problem. The problem is that if you see, we didn't think it as hexadecimal, which is the thing we are using. So yeah, that was my bad. We always have to print hexadecimal for displacements and memory addresses. So the thing that we wonder is this. Yeah. Is this F because, I mean, the one that we coded is that's interesting. Oh, you know what, let me change that because I hate it. I thought it was gonna be useful, but now I just can't stand it. So I don't want that. So there you go. Yeah, so we have a problem there, but the problem is that the formatting of the F, or the values, are minuscules, and we probably want uppercase letters, minuscules. Lowercase letters, my bad, I'm sorry. So yeah, we want uppercase letters, but sprintf prints lowercase letters. So let's see if we can change that. It shouldn't be anything harder than that. So let me go and say that let me close this. Okay, so we just need to change to X. Okay. Alright. So that was the whole story. So we just need to do that. And this is the only place where we use these ones, huh? Oh no, here as well. Here as well. And that's it. Okay. Well, in fact, this is EagleFly, test debug target, and the test lesson. Okay. There you go. So that's, it looks better now. And now, yeah, I like that. So now we format correctly our strings, and the displacements have the proper size, and we have the instructions output the proper operands. So yeah, I mean, like that. EAX in memory EX03, XM0, XM1, 0808, then resume, FLD 00044, ST1, ST0, ST0, ST1, away, EAX FF0, OP. Alright, that's good. That's good. Okay. So now that we have that, let's see what we can do. One thing that we could do, and it's like thing that we left on the last stream, is that we're playing around with the tables. So how we get the names tables, that, if that makes sense. So let's see, let's go that way. Fetch register open. So we have this instruction called get register index, and the reason that we were trying to change that is because we don't have that like properly down here. So we probably want to do that. Now I would like to do that change across with an instruction. So let me see if we can find an instruction that has, I don't know, like a special register, like a control register, which is just like, so we can see some usage code of how do we want to see this function call to be constructed. So let's try to do that. It doesn't sound any weird. So let's try to find, for example, the bound instruction has this weirdness about the operand, because it has to be two operands, which are rather 1616 or 3232. So but both have to match, and both have to be, they have this weird syntax about the bound call. So we can use the bound call. It's a really special instruction, but yeah. it's a nice try. So we can use the bound. So the bound, let's try to do the bound. So if we go into here, we have, let me zoom here so you can see better. The bound instruction, it's it has two operands that we know. And let's try to find if we have different flavors of it, you know. So if I try to find it, here you go, we have a bound. So there's just one codification, one encoding, sorry, of the bound instruction, which is this one. It's a modern byte, and its main output. So it's simple in the sense that it doesn't have like many data, but it's just I care about the operand here. So the mod has an A, which means something special. A value of 1 being bit 76 of the amount of burn bytes reserved. Okay, so that means that for this particular encoding, the mod does not mean that we are gathering something from a registered value, you know. So or this doesn't tell me that it's just 1 1. It can be 0 0 or 0 1. All the combinations for the mod fail. So yeah, I mean, that's okay. So let me go to the place where we can find something about the bound. Something about the bound. Bound instruction. Bound instruction. Bound instruction. So yeah, it's for raising exceptions for out of the array references to operands, which is nice. Let's say, I mean, it's not. I mean, something that C and C++ doesn't have in their array checking, but yeah, it's just something that we can just test normally with the size of it. But we can also use the bound instruction, which is also nice. So let's go Intel memory protection extensions. So we have a special situation here with Intel MPX, which right now we don't know what it is, but it's something to consider. It's not gonna modify bound status. Otherwise, with MPX, it's gonna modify it to and write 0 to bound status register. Okay. The bound range exceeded. The bound instruction compares the same value against upper and lower bounds, and raises the bound range exceeded exception if the value is less than the lower bound or greater than the upper bound. This instruction is useful for purposes such as checking an array index to make sure it falls within the range defined for the array. Okay. One legacy bound instruction kills a BR with Intel MPX enable. So it's a legacy instruction. That's nice. Is written with 0. That's something that we already know. That's something that we already know. The ABX ref is in a 4 by where we are. We're on the 4, man. Okay. Okay. This is ABX 512 encoding. We don't care right now about that. We don't care about that. This is the thing we're calling for M1616 and 3232. That's something that we already know. It has to be matched by a 16 memory operand. Here you go. So this is the way it works. It has a 62 on both sides, and it has an OR, which is a register, I believe. I don't remember. And instruction mnemonic or assembly language thing is a bound R16 and a memory 16, 16, and or a bound 30 with register 32 and on memory 32 and 32. So oh my god. 64-bit mode is invalid in 64-bit mode. So we probably, I mean, it's not even encodable, we may say. We have a compatibility legacy mode. It's valid. The description, check if R16 is within the bounds specified by M16, 16. Check if R32 array index is within bounds specified by M32 and 32. So we have an RM. That means that the first operand is the rec and the other is the RM. And we assume first double word is the lower bound of the array and the second double word or word is the upper bound of the array. The array index must be greater than or equal to the lower bound and less than or equal to the upper bound plus the open size in bytes. If the index So now we know, I mean, what we have. It just pretty much it's simple. I thought it was a little bit more. It had more fancy stuff there, but now we just have a register and a memory operon, and that's all. So we can just say 6062. So the math has to be, it cannot be, it has to be a memory operand. So it has to be, we can choose it as well. Now I was thinking about, well, since this is just able to be on 32-bit, that means that I mean, of course, this is not possible. You know, it would be invalid for 64-bit mode. So even if we put it on the test system, so yeah, it's not gonna be possible. So yeah, I mean, normally in 64-bit mode we wouldn't do anything but just say, hey, what's going on here? You know, we can try to skip it, or I mean, on the first place, if we have a bounce there, it's just that, or rather the assembler or the compiler faulted, you know, or you know, assembler compiler got an error there and put an invalid instruction there. So yeah, we have to, well, I mean, we're gonna disassemble it. Let's say we disassemble it with a 3232 just for keeping it simple. And yeah, and then we can check for the 1616, which is something also that we have to think about. So this is gonna be more. I mean, we're gonna think here more for how do we want to start to divide instructions on modes. You know, because if you think about it, right now, well, we have a string of instructions, but we haven't checked if it, I mean, if they are even equatable on 64-bit mode or whatever, which is the thing that we are doing right now. So we have to have a, like, I don't know, a tag system or something that tells me, hey, you know, this instruction is not possible, so try to find something to do with that, you know, like forget it, pass it, I don't know, whatever. We have to find something. So I'm gonna say here that I want, well, let's go with the 3232 as well. And yeah, so we're here, so we can say, I don't know if we can have an SIB. Can we have an SIB? A bands with an SIB. It's not, it could be, you know, we can try it, you know. So we can say that it's 100, so it's gonna be 2 2 0. Okay, and then for the SIB we're gonna have which yeah, I mean, it would be a little bit kind of weird, but we're gonna have I don't know, something simple. Something simple. Well, all of them are simple. I just want to see the kind of way that we go. So we can just say the same thing. If we go with the same thing, well, it's not encodable now. So it has to be, I want something different from EX, so we can just play around with the offsets and see something more about the table for the register stuff. So it must be, we have these special cases for the we have a base of that thing. So yeah. Mm. So let me remember. I didn't remember which ones. How was the way that it was encoded? Probably we already have it. So I just wanna find it. Yes, no. So I want, this is gonna be 0x So here we have it. We have a scale index plus a displacement. We have no base. The base normally goes first. I don't remember. We have to see it. So it was over here. Here we go. We have a base, index, scale, displacement. Okay. So this particular case is not going to have a displacement at all. So yeah. So we can just say that. Well, we can say whatever, we don't care. Normally, I mean, since we're looking like for arrays, we can choose ESI because that's for strings. I mean, this is gonna be a string or an array of strings, whatever. Or it can be normally it's ECX, as well, because it's an index for the loop or whatever. So it can be ECX as well. Well, ECX is gonna be fine, yeah. So ECX is gonna do its job. So we're gonna have 4 and this number is gonna be 4, 8. Yeah, it's 4, 8, just for taking EAX as the base. She can be, well, you just think about it. It's the scale index. It can be EAX. Well, let's play around with EBX. It's 0, 1, 1. So I'm gonna say 0, 1, 1. And now I want to remember this because it's on the 64, isn't it? Okay, so it's scale index space. Okay. Oh my god, wait me a second because my pen ran out of ink. Just hold me a second. Alright. So we're gonna say that we have a scale index and a base. All right. So we can just say, well, we're gonna have SS is gonna be 0, 1, and then we're gonna have index is gonna be 0, 0, 1, and then EVX is gonna be 0, 1, 1. So that gives us 4, 8, 11. For B, well, that is the thing. For B, I don't know why I didn't read it, the opcode itself. So for B, okay. So there you go. If we run it, we're just gonna get bananas because we don't have an encoding for that. We're not gonna find the instruction. You know, we're gonna get the entry. The entry is just gonna be nothing as we expected, and C byte now it's pointing to 20, and I was gonna think that's another instruction if we have any like that, which I don't know. We have 2, 0, but yeah, I mean it's not gonna happen anything. So well, it happens, you know. It was good that I run it because I was like thinking, well, what happens if it doesn't run? So it's gonna pass over, so it's gonna find if, you know, it's gonna go to the next one. Well, it depends on what is the interpretation of the byte. So in this case, he knew that it was a 1 byte of table, you know, so it just passed along the way and go to the next one. So now 20 should be also as well something that if any is not gonna tell us something about something different, you know. It's gonna be defaulting to the same case, 1 byte, so it's gonna be just going without anything here. Now it wouldn't be the case if we already have the encoding for that old byte specifically with the 1 byte of table or something, which in this case we don't have it. So we have to be really careful, because if we have weird bytes, we have to have or something that we don't have a special meaning for it, we have to handle it somehow, you know. We have to have a way to back up from there, you know. So let me put it as a to do because it's important. So for example, far pointers are also a thing that we have to think about as well. All right. So if we do that way, well, let me put it here. Inappropriate is like that. Inappropriate. 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 Okay. Inappropriate. Appropriate. Okay. Thank you, Google. Alright, so I was just trying to find out if it was. I mean, probably it's not necessary for a 32-bit instruction to have an SIB encoding, but you know, it's possible. We haven't found anything that tells us not to do that. So we can just say it out loud. So the first thing I would like to say is that I want to add the instruction as it is, with its proper by. this is a 1 by thing, a 1 by, which it will add to 3. In that case we'll have this thing as well, and this is a bam. There we go. And then how is this even used? Let me remember. So it's band register math. Okay. So it's rec to math. No, math to rec. Okay, math to rec. So this is gonna be false. We don't have register index things, isn't it? Or not that I remember, but it was just thinking about something different there. But yeah, we don't care about that right now. Because yeah, it's just that, for example, FLD adding 300 should have things like this. So especially for this one's just not important. Operand counts 2, yeah, 2. Memory operand size. Mnemonic name count, string length add string, and so we do that. I added it as it. I have to add it as well here. So it's a 62. And that's it, isn't it? So now at least we should try and find it out. We have what? We have an ad. It's a little bit weird. Because this is the ad advanced, yeah. And we passed the 62, sorry. So it shouldn't be at all that the case. So I want to go back and a little bit before instead encoding. So this is normal, I don't care. Continue. Oh, we didn't check. What? Oh, we changed the. Oh my god. Oh my. We got a typo there. It was a. It was a funny typo. Or is it? This is like this. So yeah, I mean this is these are all bounds, so that should be it. There you go. Now we have, I mean, we already got the correct, but the problem was like, how do you say, it's something that was misconfigured, but yeah, okay, whatever. So yeah, we got a valid entry, and you know, this is good or banana is gonna happen because we're gonna have a memory open. That's normal. It's gonna be 32. There's not gonna be, well, for this particular case we haven't done anything at all for it. It's just say, hey, we got this invalid displacement, and that shows we do. And if we fetch a register operand, which we will do because address says it's not being overridden, which it's okay, but now we have to think about this a little bit. So now we're gonna just, I mean, this is just pretty trivial, you know, adding the instruction. So now we can just try to do the other part of it, that it's the register, the SIB part, you know. Now the first part is the memory and the other is the register. The register, we already got them. We have to go for the address, you know. So the address is going to be, we know which address we have. The address is, if you remember, we define it to be it's going to be ECX times 2 plus a base. So, well, if we want to be fancy, it's going to be base plus ECX times 2, which the base is going to be EBX. So it's going to be EBX plus ECX times 2, and the displacement goes afterwards. So we already got some displacements, we already got some registers going on, which we think of them as indexes, you know. Normally they are indexes with no scaling, so that's the case. So right now we have simple indexes with displacement, so we have to add a base there and some scaling. That's pretty much it. So let's see. So I can go to fetch memory, and right here we got the displacement and we got the register open. So we want to do this twice at least, because we need 2 registers, one for the thing and this is going to be base, which is normally invalid, and an index, which normally is something invalid. Well, no, this is most of the time is gonna be 32, and right now we use the address size that's got passed along there, which is alright, you know. It's not particularly problematic. The address size itself, we just nullify it there, and then we just use it as the sign extender. And this is the displacement we use. So address size is just gonna go away now, and we're just gonna say index size and base size, which base size has to, I'm gonna say invalid, but it has to match the index size if any. So we're not gonna have a base only just if we have a, but if we have an SIB. So for SIBs have to be something like this, math I don't know. This is because we are on 32 mode. But yeah, so here we don't have any SIB. So this 32. So it has to be 04 3C or 44 7C or A4 PC, and that's all. Oh no, my bad. Yeah, because I have to count it because these are the ranges, so they go like this, they go downwards all the time. So we can just say that SIB by percent, base size 50 pass size 32, and over here we just pass the base size, and then we pass index size, and then something like that. So we have a base plus index times scale. So this is like this. right now I'm not gonna care about the index, but here we have to have a better thing to see. So I think I like more this, you know. And I like that more, so we can play around that way. And then so yeah, something like that. Now normally, well, let me see. No, okay, the scale goes afterwards. That's a little bit weird. You know, normally in mathematics you have the coefficient before the index or the before the variable. Uh, I mean, I'm not saying that it's not, it's okay, you know, because that's the way that they have it there. You know, even here, we see on the SIB, that's the way they represent it. You know, have an index times scale. So yeah, that's pretty much the way it goes. You know. So we have to push there. And here we have to push as well another value here, which is scale. Now I can use this here as well. Now I prefer it this way. So if I compile, SIB present is not, doesn't exist, that's okay. Model RAM, this is address size, this is index size. SIB condition expression to typo is illegal, that's okay. Condition expression of type is illegal. Scale, we have to get the scale as well. So before doing that, I'm just gonna say plus on the create identifier. This is gonna be symbol. Okay, so now we can do these ones. Here we did, oh, and here is the this is the this is the thing I was looking for. I'm gonna put it here. Okay, just, oh my god, can you erase that? It's just the same thing here. And Oh my Jesus Christ. Well, this is gonna be like this. Alright, so we can just implement this SIP by prism, which is gonna be we're gonna follow the table, always follow the table. And we're just gonna say that we have so it's all 5-4 5C, 6-4 6C, 7-4 7C, A4 8C, 9-4 9C, A4 AC, B4 BC, and that's all, you know. So it goes from BC 04 to AFE. So if you think about it, well, you need to, we can do that, I mean we can do this, or we can just say mothering by 0x f, and then go to then I mean here we already checked that before, but because we have 0x0 0x ff, because since we're already outside that scope, we're not gonna get that match. So could we could not check that this thing here, but just because, yeah. So in fact I can say is register brand. And that's pretty much it, yeah. And here I'm just gonna say oh, and something I was forgetting. Well, this is that here we have to return the value, you know, which is the scale. So add scale, it's gonna be something uh, it has to be well, this case is gonna be it's a scale. Where is the scale? 1, 2, 4, 8. Okay. So we have to look in the SIB itself, you know. So so we can just say that we can shift it by 6 and 0x 0x3 plus 1. And that's so she say so in this case we have this one, so we just can just, it was a little bit wonky, isn't it? What is it modern by? There you go. Oh my god. There you go. And that's all she said. Where is it? So we compile, but we have to modify the fetch register operation because we didn't finish it. So this is gonna be something similar, it's just that we have to return a result in this case. So result so that should be it, I guess. I don't see why not. It's just the same stuff. Yeah, so now we have our own fetch, it returns the value. Now on the fetch itself, here we're gonna get it, and we can return the result if we want, if we want to get a result as well. I don't see why not. And yeah, okay, so let's try to see this as as something that we can probably test. Let's go there. I don't care about that. I don't care about this. Oh my god, I didn't mean that. There you go. There you go. Well, we do that correctly. There you go. We got into here. It's not a register operand, so we just say, hey, we're gonna get into another place here, just playing around. Displacement is invalid. Yeah, we'll have a displacement. What about the SIB? We have both of them, and we can just say if it's result. What about the result? uh, so the mother and byte what's going on? It's to 0. It is to 0. Why it is to 0? Did we set it that way? Yeah, it's to 0. So this is all backwards. It has to be 2-4 or 2C, isn't it? I mean, we meant, where is this? This is the SIB. We don't care about that. So it has to be. We were saying that we wanted to test with the first one, so we didn't. Oh, okay, yeah, it was Bugus as itself. So yeah, it has to be 04 or OC, because that's the register we are looking for. So the instruction itself, let me write it because I'm gonna forget it. So it's gonna be a bounds with an SIB badge, so it's gonna be bounds some register, comma, EBX plus ECX times 2, and in here as a register we didn't choose a register, so that's the problem. So we have to choose one of these. So we can just say EAX, let's say, because the others are already occupied. So this is important because if we are using the same, it will be a little bit problematic. So yeah, let's choose AX. So it has to be 04. That was the problem. So my bad. There you go. So let me just erase that tests, compile back, and see what happens. So we're just gonna do the same stuff now. Oh, I didn't see it. Did we see it? Oh yeah, okay. So it was just passed along. So we didn't see that. I mean, we got the result and we got a skill. It's 2. That's correct. Okay, perfect. That was too fast for me. Okay. We shouldn't get anything like that. So let's go straight on here. We're gonna fetch a register open with a base size. We hit switch is 4. Yeah. So we got 4 and we got a buffer. So it's what? ESP? Oh my god. It's 4. Did we make it? Was EBX, isn't it? Ooh. The problem, of course, well, let me see. I want to get here. Recoil. Continue. There you go. So we got a proper base size, but we don't have a way to say, hey, we want the index or whatever thing. Well, let me see. We're gonna get there. So we pass the mother byte, and you see that the rec, well, with the mother byte should be 04. Okay, perfect. So they get, yeah. Oh, that's the problem. We are using the mother byte, and this is true, so we're using RM. Yeah, we haven't tested this for passing the SIB. Now RM itself is 4, and we got the operand size, it's 4. So we're gonna get offset. Well, offset is 4. And here is just something that we were not expecting at all, you know? We want to change that as well. So yeah, that's something that we were missing there. So yeah. So first of all, I would like to see the table itself. So we're going for EBX, which is 4, but we were getting ESP. Okay, so it's this one. 1, 2, 3, 4. Okay, so we have ACDB, and this is EDBX. And on the SIB, this is with the mother end, that's why we had that way. ECDV, you know. ECDV ESEVED. That's okay. You know, sometimes it won't. You know, sometimes it's, yeah, the mother has a specularity there, but that's why it was working. Yeah, I mean, it's busted because we don't handle correctly the mother M byte as well. So the mother M byte is incorrect, and the SIB, well, it's just the same case. We don't have any handling properly, and it has the same order: ECDB, EBP, ESI, EDI, and this is ECDB, and then this ESI, EDI. So this EBP is the only one that changes. See, if it's an SIB, we go for EBP. If not, we go for the displacement. Normally it's a displacement, or normally it's also EBP here as well. So EBP is normal as well. It depends on the table. For example, here we have B, 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 always B. So yeah, this is a special case. We haven't go into it. So yeah. Okay. Um. So the table, yeah, we have to change a little bit the table. Normally, yeah, the table is not gonna work that way. We have to change the table. But now we see, I mean, from this case, and for going for the SIB, now we know how we want it. You know. Well, it's not this one, but well, yeah, it's this one. Okay. So we are just about running out of time, but this is the first thing that we have to do after. So probably I can just change it manually now, and later we can just play around. So we won and if you think about it, well, the way we had it before is because we have the registers encoded this way: ECDB, ES, EB, ESI, EDI. So that's why we had the encoding that way. Which is the same, you know. We don't have ESP only, you know, so it's pretty much the same. So this is okay, I guess. We just have to solve it, you know. M0 and here is just the same: ECDB, EBPSI, EDI, ECDB, EBPSI, EDI. Just the SP is not encodable. So it should work, isn't it? I mean, now I see it, now I think about it. I thought I was reading another thing here. So let's try to do it. It should work. So let's go back into fetch memory. Well, fetch register. So instead, the only problem, yeah, I mean, the only thing they had to think about is that we are not reading the modem anymore, you know. It shouldn't, at least, you know. So it just has to solve for the where is it? I mean, fetch register operand, it's okay, or is it? Yeah, this one. But we want a support function here. Let's say, which what register index could be, you know, it's something good. It's just that in this case we passed rmrec, you know, we are using the rmrec. So we can just say, hey, now we're using 1 here, and this is pretty much it. So we can just do that. Well, there we go. What's this? I don't know, it doesn't matter. It was like something thinking about, but later on was just nothing. This is the result, and we want the offset to be passed as well. So, well, this is not offset, it's just the row index, row index. We'll need that as well now, just like that. And yeah, fetch register operand. Yeah. Something like that. Well, and um so we basically want something like this. In this case, we are not gonna have an RM or rec, but we have pretty much a way with the SS and the index. Well, more like the index, yeah. And we also have the SIB, which we can also, sorry, the base. We gotta get the base, so we can just say, the problem is that we're gonna overpass it of fetch count. It's gonna do bananas, you know. So this is not something that we want to do here. It's something that we want to do here. Or something that we want to do here. And in that way we just return, we take that out, so now it's getting more and more independent, which is nice. In this case we have an index in the base, and we got well, SIB by SIB by, this is the index, this is the base, and fetch RM field. Well, this is not fetch RM field anymore, but you get the idea. So this is, yeah, the base or the index. Yeah, you get the idea. And you know, this is pretty much the same. I mean, we don't need this anymore, so I was just like thinking about this. This is the index, and this is the offset, which I prefer row index, I guess. Row index. No. There you go. We got it. We got it. And yeah, so EAX, ECX, EDX, EDX, and it's the same here as well. EAX, ECX, EDX, EDX, ESP. Now here we can use ESP and stuff like that. So we have a to do there. Here, check for valid registers that can be encoded. And this goes as well for this case, but you get the idea. You get the idea. So let me compile that. So fetch mother and bind, it has to be a flag that we pass as well. Fetch mother and bind. It's gonna be true. Well, it's gonna be false. No, I prefer it to be passed because I wanna assert that. And that's pretty much it. Fetch SIB by, well, can do that. SIB by, it's not put it, so we can just say that SIB byte mother and by and there you go. Okay, so now let's try this out. We took out the counter, so we can do this as many times as we want, or from the other side. So whenever we do it from the outsiders, it should go and work. If we, and yeah, I mean this is a little bit tricky, but you could do it that way. We can try to do something different here. But yeah, this is the place where we want to do that. And where is it? Where is the other one that we were also doing? Yeah, I think oh, and the memory one, yeah. So this is the important one because we can fetch it and just go into it straight, so we have to count it. So if we are gonna count it anyway, we can just say this. And that will be all. Now let me check it. So we're gonna have this, and we're gonna have this. Yeah, that's better. And yeah, that's the match, isn't it? Yeah. Yeah, that's the match. Alright. So if I compile, I can do that. And let's see what happens. So let's run this one more time. We're gonna fetch a memory operand, and mother and bytes, placement, effective byte size invalid. This is gonna be correct. We have an SIB by. We have we don't have that. I'm gonna push a string. Oh, and that was weird. Oh yeah, my bad. Oh, yeah, because too bad. So never ever. That was a tricky thing, isn't it? Like, hey, we have a boolean, but since it's the same type, we can't just use that as a boolean. So we don't want to do that. So it has to be this. And this well, let me put it here, both right here. Fetch SIB by, fetch modern by, and fetch and fill. Just the same thing. So here it goes, fetch modern by, fetch and fill. This is the thing that we should pass. So now I think about it, let me go to this thing, fetch register operand, and I don't want to have this, I have to pass it, because now this is gonna be bananas. So I want to see the errors, and here I have to go and fetch modern byte and fetch and fill. So I have to pass it here as well. Fetch mod and byte, which is normally the case, but now here we want to pass fetch modern by and fetch and fill flags. So fetch motherboard bytes, here is going to be true, and here we are how we were using the iron field. This is what's true, isn't it? Okay. So if you see here, we probably want some flagging system. Well, first I'm gonna do it the large way, and later we can do it the compact way. You know, always using compression oriented programming. So yeah. So yeah, we're gonna pass the flags, mother and by, fetch and field. All of them have to be true. And here we are gonna do it's gonna be false, and iron field has to be true. I don't know. Well, it has to be true. This for the base, isn't it? So yeah, we have to be true, and then here it has to be false. Yeah. Fetch modern by, fetch iron field, and that's it. Then here, that's all she said. Let's compile. And here we have a fetch register open. We're gonna say that fetch by, fetch iron field, to fetch modern by, fetch iron field, and fetch modern by is gonna be true here, and fetch iron field is gonna be false. And I think that's okay, isn't it? I don't know, we'll have to see. I remember, yeah, it was false here, and it was true here. And then it was, yeah, this is fetch iron field, which is true for both cases. And then downwards on the third case scenario, we have true, false, false. A bunch of flagging. Of course, this is totally error prone, but wait me a second, and we're gonna change it to a more compact way. So we're gonna do that. So let's pretty much run it. We have an SIB by, modern by plus 1. It's 4B. It's correct. Index it's 01 and the base is 03, and we're gonna fetch the base. In this case, bits can reverse, there you go. Yeah, that's correct, it's EVX. There you go, push EVX plus, then we change the RN field to false to get the other one, and just say, well, same stuff. We're gonna get the index now, which is 1, and it should be ECX, that's correct. Times now the scale what value is 2. Okay, that's perfect. 2. There you go, ABX plus ECX times 2. Yeah, that's correct. Operand offset displacement plus 1. There you go. Well, yeah, displace operand okay. So we have the memory one. Now we got for the register. In this case, we pass modern bytes through RN field. It should be false. Okay. So, oh, what happened there? Oh, the entry operand count is not a thing. So how many does the entry just have 1? We set it to 2, isn't it? Okay, initialize a table for bound. Oh no, oh my bad, this is we do it all. Oh my god, this we did it all incorrect, isn't it? So this is just so this is the correct thing, and this is the add string. This is add entry. That was weird. Super weird typo. And this is the bounce. There you go. So that's more better. Add stream. I believe that's the only thing we changed, but we're gonna check it out later. And now this is incorrect now because this is the bound string. There you go. Okay, so one more time. So the entry, it's a bound. Okay, that's correct. Now it has the correct data. It doesn't have a motherm. It does have a motherm. So we do banana. We totally spill out the add entry. So let's do it one more time. This is false. Open equals 2. This is door that's correct. And immediate is invalid. This is correct. Okay. And this has to be something I don't remember. The load instruction doesn't have a motherm, isn't it? Because it has an immediate, but that's all. So this is false. This is no, it doesn't matter because it's just one operand. So it's 1. It doesn't have that. So yeah, memory operand size, register operand size. This we keep it that way, but the immediate size is correct. String length, yeah, that's correct. This is gonna be I don't remember, but let's say we have a word because it was a memory operand. I don't remember at all. So it does have some mother entry, isn't it? Oh my bad. Well, yeah, it was something like that. And yeah, it has the immediate. It was just the immediate, isn't it? So yeah, this is invalid. Okay. So it had, I don't remember. I'm totally busted here, but if it does has it's like no, it doesn't have. I now remember. It doesn't. Okay. So now it should be okay. You have an add, by, invalid, 1, false, okay. And this is true, false, data, door, invalid, bound. Okay. Compile. And I think we're gonna just run it and see what happens. There you go. True, false, door, data size, invalid, 2. Okay. There you go. Let's see the man buffer. That's correct. There you go. There you go. You get the rec. What about the error fields false? So we get the rec, and the rec tells us that we have a 0. Now the motherm by is pointing to 04. That means we're getting from EAX. That's correct. And effective operand size is 4, so we get something that, yeah, EAX. Okay. Disassembling state, fetch count. There we go. Return result. And immediate. We don't have immediates, so I'm sorry. Okay, so we have a bound EAX, EBX plus ECX times 2, comma, immediate, nothing. Okay, perfect. So let's see what happens to the other instructions just because for fun. This is and now, well, where is the pointer now? I think it's probably the pointer, the prime. Okay. Jesus. Okay, so I gotta go right now, but at least we know that we have that instruction correct. We just have to check the other instructions as well, because I just want to see if the pointer is the problem where we're pointing to 4B. So yeah, that's the problem. We're pointing towards something incorrect. So 4B, that's because we have an SIB, but we haven't considered that. So that can be easy to do. We can just do it fast here. This is gonna be the last thing we do. I'm just gonna say that fetch memory operand we say that it was displacement plus SIB present now. Well, I'm gonna call it this is so see by now it's pointing towards 80, which is the next instruction. That's correct. This is an ad. SIB by person. Now we have a scale. Why do we have a scale? Did we enter here as well? That was weird, isn't it? Where's the scale? This is the scale. So we have busted the scale. We probably have busted the scale. So yeah. Well, we have to check that later. Let me put it to there. Well, I'm just gonna do that because they're like this super simple stuff that we can do this. One more time. There we go. Mother and byte. We have 40. 40 is, yeah, it's this one. That's correct. So if we enter, right now the scale is null. Okay. Oh yeah. The problem is that we don't check it. We just say, hey, we're gonna get the out scale, and that's all you say. That's totally bogus. So we have to say if the encoding or the instruction has, I mean, this is probably, it's a bug that we can easily solve it. SIB present. SIB present where it is. It's not called SIB present. SIB. Yeah, SIB by present. Okay, my bad. In fact, we can do fancy here. We have ESI. It's a little bit weird, isn't it? Oh, okay. Oh, yeah. It's because we have to go back and have a different testing there. But yeah, I'm gonna leave it that way because I know what to do there. It's a little transformation, but yeah, I put it. All right. So thank you very much for coming up on this stream. Please, if you have any questions, post them on Twitter or YouTube, and I'll be there to answer. Yeah. Please, the questions make them relative to the thing we did today, so I can just answer them straightforwardly. And yeah. So thank you very much, and I will see you all on the next stream.